Thank
I
you.
can see a lot.
Thank you, Ishwita ma'am, for your beautiful presentation and sharing. Thank you. There are many more questions for you. Can
Yes,
I
I can
put
see.
this?
Scrolling. Uh,
I can read for you. Hello?
So I found one. Why the study experiments on neutrino is so much important. So much money is spent on its study. Why so? I think this question is valid for not just like neutrino, like all experiments. Like if you look at the amount of money they spent in CERN to detect Higgs boson, and now we detected, Higgs boson, and so now we'll be like, okay, so what happened after detecting Higgs boson? So as I said, the story about the general relativity with Einstein, right? So we need to know the physics first to come up with the use of it, the technology. I mean, I can't just say like, oh, we're just curious, so we need to find all these things. No, I mean, there is, and it's not just that. Like, so research for a country is also viable economically. For example, in CERN, they were trying to detect, they were trying to find the Higgs boson for such a long time. On the way, they invented the so-called, not so-called, the World Wide Web. So the internet, we're talking now and everything fun happening, Netflix, Amazon and everything, Facebook and everything is because the research will spend on money on Higgs boson. So Timothy Berners-Lee is the person who actually built a web so that scientists can collaborate with each other. And that's how we have the internet today. So these kind of research, when you have a big goal, you just don't have one goal, you have many goals. So it's going to help the country progress technologically also. And that's how your country's economy and everything will also strengthen. So if you have the best computer software or AI or machine learning, which can predict different things in your stock market and stuff like that, so then your country will have an advantage, because now what's happening in these experiments is that you have a number of huge data, right? All these huge data, you have to like communicate with each other and everything. So nowadays speed is a very important thing, and this will also help in kind of not cheating, getting an advantage in stock market. So like it gets morning in China first, so why not send a signal to US before the day starts, about the changes in the stock. And it will depend who sends it first, right? So how fast will you send the message, the communication? So these scientific goals, so whether it's a neutrino experiment or it's a dark matter experiment, don't have immediate uses in the technology because we don't know many things about it. Once we know what it is, we can think about what to do with it. But on the way, we are going to improve a lot of technology. And that's just one of the examples about the internet. Okay, next. Is there any relation between dark matter and expanding universe? Yes, so, okay, by relation, we can see that, it has given us like evidence. Because the universe, we know, because the universe is expanding and everything, but more it is about dark energy, like dark energy. Actually, I can hear my husband saying dark energy. So in fact, you can help me answer questions. So he's the expert in these kind of things, like the theory ones. Next, how is dark matter from another dimension? It's going to be, definitely it's in this dimension which we are in, like these dimensions. But okay, so if you talk about dimensions, it's more like, you're thinking about string theory, I guess, because they work with like 14 dimensions. And they do have, string theory has a way to like explain the formation of dark matter. So I don't know there are any other dimensions or not, but in this dimension it is there, and we need to, it'll be, I think, easier to detect in this dimension. Okay, so how's the temperature difference of 2.7 Kelvin in CMB calculated? Oh, 2.7 Kelvin. That's the Hubble telescope. Just the temperature. That's yeah. So basically, we measure the wavelength of the light, right? These are like photons, right? These are packets of light. So we're measuring the energy of it, and then we calculate the frequency and we get the temperature. So there are a lot of experiments. I think the Planck telescope, they are the ones who are measuring. Most recent one is like 2015 is Planck. I don't anything. how did the dark matter originate? Yes, that is thing you mentioned. Like, we believe there are many theories that believe that they originated with other matter, with the Big Bang, and we also predict how they must have evolved to the state which we can see them now. Then, so how did they originate? Yeah, basically, we believe that they existed at the same as how everything else got formed at the beginning of the universe. Like, we started with the Big Bang and the hot plasma. So that's also, so we, in fact, the theories, cosmological theories, they work with models like, field theories. So basically, field theory starts. They'll work with some fields which evolve into matter, antimatter, and dark matter, all these things. So they're different kind of fields responsible. They can be like scalar fields and other fields. So just like quantum, like if you watch some YouTube videos on quantum field theories, so they'll explain how field theory is used to describe the origin of matter. Okay, then could there exist a whole dark matter universe? I mean, the whole universe has dark matter. Like, only dark matter? Okay, I don't know if there is like more than one universe. I mean, we do see in like science fiction novels and movies that there can be like multiple universes. There is no evidence about it. And I don't have an opinion whether we have more than one universe. But in this universe, there is dark matter. And if there is multiple universe, then why not a universe where there is only dark matter? Okay, does dark matter exist in every galaxy? Yes. Could it be that dark matter is the space-time matrix itself? Because the only interaction we have is through gravity. Yes, so this is actually the modified Newtonian gravity I was talking about. This is what everyone thought initially, right? Because the discrepancy came in the calculation using the gravitational theory. So if it is something to do with space-time, because gravity, yes, you must, we'll talk about gravitational waves later. But gravitational waves has to deal with space-time and all. So they thought, so they did come up with very complicated modified Newtonian dynamics theories. They are called MOND, and people have been working for many years. But this theory is not able to explain all the evidence. It's not just that there's a difference of mass. There are other evidences like large scale cluster formation and all those things. So everything, like the theory should have been able to, explain everything. I don't think so there's any proof. Nowadays, the modified Newtonian dynamics, it just looks like one of your super complicated mathematical theories with a lot of parameters and all. It's no longer simplified. It became something else. Okay, what is dark energy? Now, dark energy, it's actually started with I won't say started, I mean, like, it kind of got verified later. We didn't talk about the lambda CDM model, so we didn't go into much of cosmology theory in this talk. But Einstein's theory of relativity he thought it was a blunder, like he had an extra term kind of, which he said was responsible for the expansion of the universe, because I think he had trouble believing that it was accelerating also. But so this is something in the background, like which is there in the universe. This kind of energy is form of energy, which we don't know much about. But we can see the effects when we observe the expansion of the universe with our giant telescopes and light surveys. Can ordinary particles decay into dark matter? Yes. This is the belief of the collider physicists, particle physicists. They believe that if they are colliding known particles, like your ordinary particles, and they hope that they'll give dark matter. I mean, CERN hoped that they would have seen some fancy particles. Unfortunately, even in 13 eV, they were like, many supersymmetry people were disappointed because no super particles were observed. I think like a whole generation of scientists were disappointed with it, because everyone was looking forward to the high energy experiment. Yes, we hope they decay into dark matter and we can observe it, because if they do, which is less chance, I mean, we have to go to really high energies now. Does dark matter emit any radiation, and can ordinary particles decay? Okay, it's the same thing. If they did radiate any kind of, radiation, like which interacts with our electromagnetic force and all, we would have been able to like detect it easier. So right now, also the thing is, like, we don't know much about gravity. We don't know the force carrier of gravity, because all other forces have a carrier. So So we don't know about that kind of a radiation. Yeah, but we can't use the word radiation because radiation is more related with electromagnetic force. Next, how to detect if it passes through matter, does not interact electrically and interacts with themselves, maybe interacts with themselves. There could be multiple particles that don't interact with mass and charge. Again, can we say that it's a group of particles? Yes, actually, we believe it's not just, we believe it's a dark sector. Like it's not just one particle which is not interacting. We believe there are like group of particles, like how we have the light sector, let's call it light sector, the standard model of physics. So we believe there are like many particles which are not interacting. And we're trying to like detect any one of them first. Maybe if we find one, then we'll be able to know the physics by how it is interacting with your known particles, which will help us to build the carrier particle, build the whole theory with the dark sector. And with how to, yeah, so basically we're looking at the energy deposition, energy measurement in the detectors, as I talked in the later part of my slides. Like we're looking at the phonon energy, that is how the heat is traveling through it. We're measuring the ionization, and we're looking at the interaction it has with the nucleus of the material by looking at the recoil. So we're looking at phonons and ionization. That's why like we are not using the word photons, because if it was photons, we could see its light and like things would have been easy. So that's why we are taking the help of phonons. Why do we need particles to be associated with dark matter? Yeah, this is actually just a theory. Like maybe they are associated with dark matter or they are not. Like there may not be any, but it's highly likely that there is a particle which is communicating of particles, but as likely they may be completely separate. Dark matter is attributed to the unexplained gravitational pull, whereas dark energy is the gravitational push to expand the universe. Both of, yeah, that's actually correct. That's really nicely written. Both of them are associated with gravity. Yes. Can trying to understand and explore gravity more minutely from where Einstein has left can solve this 95%. Yeah, that was the attraction of physicists after Einstein. I mean, because gravity would have solved both the problems actually. And unfortunately, people have tried to come up with so much theories, complicated. Now, as I said, the theory just looks more and more complicated now because it's not able to explain all this evidence we have, right? It's not able to explain all the cosmological evidence or the observable evidence. But yes, that was the first attraction because gravity is the common thing between dark energy and dark matter. So maybe like, just make it more fancy. And so modified Newtonian dynamics is accepted by majority that, but it's still it's a very attracting concept still, especially for people. I mean, I still have a lot of professors in my department who believe that there is no dark matter and it's just modified Newtonian dynamics and there's actually one of them is in my committee. Yeah, so it'll be fun to present to him because he doesn't think at all that there is dark matter. He's old also, so that's also one of the things. Like the old scientists believe there's a modified Newtonian gravity. Okay, so what are the maths you require in your daily life while you are doing these experiments? What are the maths? So I think maths is more like a language of physics. It's just maths. I try to not write any kind of equations because all these things I talked about, like the cross sections or the phonon heat, all this ionization, all this electron recoil, nuclear recoil, all these are actually giant equations which I did not write. And you start learning about them. I think you'll have some courses which are like mathematical physics courses like I had in your undergrad. So you start with, obviously you start with vectors, matrices, linear algebra, and then you move on to tensors and everything. Tensors will be mostly required for cosmology, like in large scale. But yes, you do need to have a knowledge of it. Actually, you do need to have complete knowledge of it to study general theory of relativity. Yeah, a lot of math, only maths. And then like even your algorithms, all the computer algorithm scripts and everything needs a lot of maths. Ice cube detector detects neutrinos. Can they also detect dark matter? So yes, there is this ice cube. Ice cube detectors are the ones which are they're in the collaboration with the University of Madison. They're in the pole. polar, yeah, they're very cheap because there's already ice in your. So they thought they could detect dark matter. I think because initially when you're going to ask money with the organization, you need to put many goals. So one of their goals was to detect dark matter, but their sensitivity is like, I mean, it's not that great for dark matter detection. Then, are all the hidden forces behind this visible existence is dark matter? No, then what must be the parameters? It is worse. I think we just call it dark matter because it's dark. I really think they could have come up with better name, but this is a very vague name because we have really vague knowledge about it. I guess that's why. I would love to know the possible parameters. Those might be responsible for expanding universe. Yes, so as I said, my talk is not to concentrate on the cosmological models that actually describes or predicts the origin and evolution of the dark matter and dark energy in the universe. We have the lambda CDM, lambda cold dark matter model and all those things. And yeah, and my husband is actually the one who can talk more about it. And I did find them interesting at the beginning, and then like it was just like there's so many models I need to detect or find out which one is correct. It happened like that. Okay, yeah. So I would suggest you to look at a lot of YouTube videos, especially by PBS Spacetime. They have a series of videos about dark matter, cosmology, and astrophysics, which are explained very in a simplified manner. And there is actually Introduction to Cosmology for undergrads, or many books. I can send some links later. Why dark matter can't be a part of the galaxy itself? It is a part of the galaxy. Like it is inside the galaxy. I mean, it can be here also. Like as I said, there might be like dark matter particles flowing through us. And then, what is dark fluid? Actually, what is? I've not heard of it. We can talk about the energy and all. Like there is fluid dynamics involved, but yeah, there's nothing specifically called dark fluid. And neutron background. We mentioned about a neutron background. I want to ask a little of today's topic, but related question. Okay, what's your take on the discrepancy of neutron decay of about 10 seconds observed in different experiments? It often gets associated with the dark matter of this universe. I think you mean neutrino decay. I mean not decay. I mean neutrinos. What's the neutron decay?
I think it's
of about. You can come in.
It's hypothesized, but it's not.
Yeah, it's actually it's one of the hypothetical theories. So I did work in the ITER experiment also. That's how actually. So basically, my husband started as a nuclear engineer. So I was working with him. It was his nuclear activation code, and I would suggest neutrino is like the closest as a candidate. Like many people, there are many theories which predict that some kind of neutrino is a candidate for dark matter. And it's not. It's more like a hypothesis, like theory. Prediction. It's more like a prediction. Okay, there are some compliments also. Thank you. How does or will gravitational wave observed around the world help in the study of dark matter? I hope a lot. I mean, I hope like gravitational waves answer a lot of questions. First of all, they are like gravitational waves related with gravity, because this whole thing is about gravity. And also because gravitational waves has given us a new set of eyes to study the universe. Because gravitational waves are ripples in space-time. Now, space-time, like you can imagine like a cloth, which is a space time. Okay, it represents a space-time. Let's go two-dimensional for 1 second. And then if you have a piece of spreadsheet or a cloth tightly connected to the walls, and then you place different objects of different masses in the on the cloth. So the heavier the mass is, the more the depression of the bed sheet will be, and for lighter particles it will be less. So you can imagine something like that, which is not a good way, but something to. So this is how they think like gravity and mass of the objects are associated. Now, gravitational waves happens and they're causing ripples in the space time. So imagine like two heavy balls on the bed sheet collide. So they are going to like send some kind of waves through the bed sheets. So this thing happens when really massive astronomical objects like black holes and all this, they collide with each other. So they send ripples throughout the space. And now these collisions have happened a long time ago, like thousands of years ago. And but we detect them now. That means we're looking at the universe, which was that old. And this has given us a completely different, not new, just like completely different set of eyes at the sky. So hopefully they answer the origin of the dark matter also, because the more we know about the old universe, how the universe was when it was young, the more we will know about the origin of matter. Okay, next. Is there any relation between dark matter and expanding universe? I think there was a similar. Dark energy is the one which actually relates, causes the expansion. Yes, so I think I'm calling my husband to join us. So, because as I said, he's the theoretical expert right now. I mean, I was. Now it's him. Okay.
Hi.
Yeah. So this is my spouse. You can find this second. Sai Chaitanya Darepalli. So both of us are going to third year PhD students, but he's from University of Wisconsin-Madison. Okay, so the question was, yeah, so they have asked again about the dark matter and expansion.
Okay, the expansion of the universe as such is dictated by the dark energy content. You can imagine something like this. To take a universe, and now the universe is actually just space-time fabric. So you have space, which has 3 dimensions, and then time, which is 1 dimension. 3 plus 1 is 4 dimensions. So we always say that space-time is 4 dimensions. And so with the Big Bang, we can say the universe came into existence, and now we have a space and time. All of this has to, so that's the birth of the universe in one way, if you want to say that way. So now we have 3 plus 1 dimensions. Apart from space time, there are also particles in the space. Those particles are what constitute the other part of the universe. So when we talk about universe, we talk about 2 things. We talk about the space time and the particles that within the space-time. So the space-time has energy. So you do not think that space-time is something like a void. It is a void, but that void, because as the space goes, she's already said that the universe is expanding, and the universe is expanding due to the energy content within the universe. Now, the space-time itself has a universe that is also termed as a dark energy in this case. It's called dark. So the term dark comes from the fact that we do not know much about it. If something is completely known, we will want to call it what exactly it is, but in case of dark matter and dark energy, we don't actually know much about them. So that's why we call them dark in this case. So so the total energy of, if you assume that the total energy of universe is about 100 in case of like 100%, then about 80% of energy right now at this point of time is dark energy, and that is because the universe has expanded. Every time universe expands, the amount of energy keeps increasing. The dark energy keeps increasing, and the dark energy is what pushes the universe or accelerates the universe to even greater and greater lengths. And out of the remaining 20%, which is remaining which is the matter in that case, about 75% is 80% is what you say is dark matter, and the remaining 20% is just what we call as the normal matter.
Okay, so those are the list of questions which were asked. So that's a repetition. So now we have this sound. So is there any particular reason for the abundance of dark matter than the normal matter? Yes, there are so many reasons. I mean, predicted reasons. We don't know which one is correct. So which theory would you want to talk about? Which tells us why is there so much dark matter? I mean, actually, we can't compare like with the normal matter. I mean, we know an estimate. I mean, we know the correct estimate between matter and antimatter in the universe, and we have theories about why.
Yeah, in order to understand why there is more dark matter compared to the normal matter right now, we'll have to understand the dark matter doesn't interact much. So when you say it is weakly interacting, it is very, very weakly interacting. And when you look at the universe, the theory of cosmology, so the theory of cosmology actually tells you how the universe began and how has it So from the starting of the universe to what we see today, the entire evolution of the universe is given by the theory of cosmology. Now that theory predicts that since the dark matter, so initially we had dark matter, we had photons, which we also call radiation, and we also call something like matter, which is the normal matter, like electrons, protons, neutrons, and everything else that we see. Everything else that interacts with light is kind of known as, is the known sector, which is the standard model, and that doesn't interact is called dark matter. That which doesn't interact with light is unknown to us even to this date is called dark matter. That is the definition of dark matter in a very discrete manner, if you want to say. So because dark matter did not interact, so initially everything was interacting with each other, and as the universe expanded, dark matter was the first one which used out of this entire interaction mechanism, and that is why it has a much larger content compared to everything else. I wouldn't want to go into more details of the theory because that would require knowing what freeze out is and then how the universe expanded, and it also involves so you have the inflation and then everything else begins from inflation onwards. So
okay, then does Higgs bosons generate mass in non-baryonic dark matter particles? So yes, we do think the prediction is correct. Like we do hope that Higgs boson is responsible the same way it is responsible for the mass in a standard model of particles. We also have theories which predict there will be something like Higgs boson, like a dark Higgs boson, like something like a particle. They're completely different. Is there any catalog of proposed candidates which are basically yes, I don't know if there's a catalog. Like you can, there are not many experiments, so I think you can just go through the experiments and look at the candidates. But everyone is looking for the WIMP. So WIMP is a very popular candidate. Everyone's working for it.
Yeah, there's a huge spectrum as far as dark matters are concerned. So because we do not know anything much about what a dark matter exactly is, there's a huge spectrum. And in that case, some people say it can be primordial black holes. Now, black hole by itself, we know what exactly black hole is. It's a singularity in the space-time as given by general relativity, Einstein's general relativity. And black holes detected recently, I think last year, yeah, the photo of black hole was actually released. And so when I say primordial black hole, those are the black holes which were formed during the early stages of the universe. So when universe was very, very young in that case. So during that time when in universe was quite infant, there could have been some black holes which were formed. One of my working topics is also regarding primordial black holes, and another friend of mine is also working on primordial black holes. So those black holes, if they exist to this state, they can actually contribute to dark matter. So in that case, the mass of these black holes is about now technically a normal black hole is supposed to be very massive. Now primordial black holes need not be very, very massive. They can have a mass only about 100 kg, and yet they are black holes. Now, why they are black holes is a completely different issue. Why even a 100 kg or 1,000 kg mass can actually still be a black hole? This is completely different because mass doesn't. It's not just the mass decides what exactly a black hole is. There are many other aspects of what you should actually define, how you should actually define a black hole. Now that is one range. There are other and then if you come to the quantum mechanical, field theory particles, in that case, the fundamental particles, which we call. So in that case, we have what is called WIMP. So these are weakly interacting massive particles. They have so there's an entire category. They have been theorized to be about 100 GeV. I'm not sure if you are aware of the units. In particle physics, we use in grams because kgs and grams is very huge for a single particle. So we always talk in terms of EV and GeVs. So you can go back, ask your professor what exactly a GeV and MeV is.
Like energy units.
Energy units.
About them in energy units, the natural units.
Exactly. And on the very lighter ones, some people say neutrino can also be a dark matter candidate. People are trying to search for it, but it'll have to be very cold. A hot neutrino cannot actually be a candidate for a dark matter. Then there is axions, and axions are one of the most debated particles for the dark matter. and they have very, very small mass, about 0.0025 eV. They're much lesser than anything.
I like to call them as imaginary particles because we had just imagined.
Mm-hmm.
So yeah, if primordial black holes are the case, then that means the direct detection experiments won't work because they're not on Earth. So only the experiments which are observing the universe and studying them will give us more information about it. And then obviously we have a separate category of neutrino experiments because there are theory models which predict that neutrinos can be, some kind of neutrinos can be candidate for dark matter.
In fact, the experiment in Italy, which recently said that they have the xenon experiment, everyone is saying that it is actually the axions which are detected by them. Because axion not only solves a problem with the dark matter, axion also solves one of the most important problems in quantum field in quantum chromodynamics, and it is important in order to ensure that everything what we know about QCD and QRT is important.
So quantum chromodynamics, study of protons. Okay. Any highlight on the theory or experiment collaboration on dark matter studies from Indian counterpart? Yes, so as I said, the Super CDMS has NISA. We have Mohanty sir, whose group is working with the collaboration. And they are the ones who send students, like their PhD students, they travel to Canada and US and everywhere else to work with the collaboration. That's the experimental side, and then we also have theory. Yeah, theory side is from everywhere. I mean, we have where I work before coming to US in the Physical Research Laboratory in Ahmedabad. So that's under Department of Space in India. There are cosmologists there who work.
India, the Indian academic sector is a hotbed for theorists. So India has lots of theorists, and
we don't have an experiment.
We don't have many experimentalists because that requires lots and lots of funding and lots of money.
And then there's like so many politics going on. We couldn't even start up the neutrinos. It's difficult. I mean, like we are struggling with a lot of things. So there are actually less experiments. This was like a topic in one of the conferences. Like, why do countries like India have less experiments going on? Yeah, like more sociological topic. Then what else? Is there a relationship between dark matter and antimatter? I mean, we are hoping dark matter has relationship with all matter, but there is no. I don't think there is any theory. There's no, because antimatter is like less. Yeah, things. I mean they are different things. So as they're in a relation, we don't know. Okay. Is it possible to explain gravitation by Higgs bosons? In what way? They are like graviton?
I think when you're asking this question, probably you're confused about what exactly gravity is and how Higgs boson interacts. So Higgs boson doesn't give rise to gravity. Gravity is completely different. So as by the current understanding of Einstein's general relativity, gravity is actually a role which is played by the molding of the fabric of space-time, and that is affected by the mass. So those are completely different things. Higgs boson gives mass. It gives mass to all the fundamental particles, but that doesn't give it. It otherwise plays no direct role with the gravity.
Maybe they ask we do have a theoretical particle graviton, which we think is the force carrier for gravity.
Gravitons can interact with Higgs particles.
Yeah, so I think that's what they meant. Okay, and then does dark matter interact with black holes? So this is similar to that question, like, or not similar. I mean, like this is what he said about like primordial black holes can themselves be dark matter candidates. I don't know if they interact with black holes directly.
They will have to be primordial.
Yeah, they'll have to be like light.
Stage.
Yeah, they're beginning of the life of a black hole. Okay. Dark matter inside our body. Yeah, they must be passing through if they are like they are part of the galaxy. We might, I mean, if we can detect them on Earth, like how we have CMB passing through us, we can also have them because they're weakly interacting, right? Because we won't be able to know, like they're not going to give us something.
One question which says, how is the temperature difference of 2.7 in CMB calculated? It's not the temperature difference of 2.7. CMB, so imagine this way. So the entire universe is permeated by a radiation. It's called a background radiation, and that radiation has a certain frequency. Every radiation has to have a certain frequency and wavelength. Because that radiation has been traveling since the beginning of time, not exactly since the beginning of time, you can say about 300,000 years after the formation of universe. There are theories and they are complete, and it's kind of proven right now. And based on that, currently that photon which was emitted 300,000 years at the beginning of universe right now has a temperature roughly 2.7 Kelvin. So the background radiation that we observe in the universe right now has 2.7 Kelvin, and this radiation is permeating everything.
Old.
And because it's 2.7 Kelvin, if you convert that into wavelength and frequency, it comes about to be microwave. So that is why it is called a microwave background.
Frequency. The frequency is in the microwave range.
Microwave range.
So this is a remnant. That's why the word background is there. So it's the universe cooled down.
It gives us idea of what the universe looked like very early in its stage, about 300,000 years ago.
That's how it originated, and it's cooled down. The universe has cooled down because of the expansion. That's why it's just 2.7 Kelvin. Dark matter is related to Minkowski spacetime. Again, I think it's referring to the concept of gravity again.
Oh no, Minkowski spacetime, dark matter and everything. So Minkowski spacetime is something different, and then dark matter is completely different in this case.
Or you can think about like gravity from spacetime, and maybe. So that's why like people try to come up with theories related to gravity and try to explain, but then no one has had a successful theory yet.
Minkowski spacetime will actually be the metric for the flat universe that we actually live in. So right now the universe can have a curvature depending on whether it's an open universe, closed universe, or a flat universe. Through all the calculations, we have observed that our universe is flat, and if you know some bit of special relativity or maybe general relativity, then you can understand what Minkowski metric is. And a flat universe requires a Minkowski metric. It lives in a Minkowski metric in that case, but that is completely different from what dark matter is.
Yeah, I think they're describing the space-time, the flat Minkowski. That's the metric used for cosmology. Is there any relation between dark matter and ether? There is no ether. I mean, that's what the Michelson-Morley experiment. They tried. I mean, they started with detecting, like they thought they will find ether, but instead they found the expansion of the universe. Like the proof that the universe is expanding. There's nothing in the background. So there is no relation because ether is like it's proof there is no ether. I mean, that's how like they came up with the expansion of universe and everything. It's accelerated expansion. Current vacuum. Yes, dark energy is related with the expansion of universe. Current vacuum density is very low. Then how dark energy expanded the universe? This is like so much theoretical.
Yeah.
In inflationary ways. To talk about inflation first.
This is why this is one of the contentions of the current studies and theories. So when you say that the current the vacuum energy in fact is very low, and that is completely fine. The amount of which is what the issue is right now. We haven't been able to completely explain what dark energy. So dark energy is actually the energy content of the fabric of space-time. But how do we relate that to the vacuum energy? That is completely is something which people are still working on, because that is not completely explainable as of now. And even if you go to the quantum field theory, so using quantum field theory, we can actually predict what the vacuum energy is at present. And there's a huge scale difference. People say that there's about 10 to the power 120 scale difference between dark energy and the cosmological the lambda, which is called the cosmological constant.
Yes, I think we should talk about inflation also. I didn't cover the origin of the universe. There's a timeline, how the universe evolved, and a lot of physics. Does dark matter expected to have mass, or they are energy vibrations? Oh no, we hope they are mass. They are like heavier, like 10 times heavier than protons, the experiment which they're trying to detect. So they are like, so basically they're like massive for a fundamental particle. Because proton itself is not fundamental, it's made up of quarks. And something 10 times as heavy as proton to be a fundamental particle is pretty massive. Is there any proof of existence of dark matter?
Lots and lots of empirical proof. One of the first empirical proofs was actually done by Fritz Zwicky, which she mentioned in the beginning. Zwicky observed that when, for example, take the case of Milky Way, our own galaxy. So if you consider any solid object, that solid object, if it is rotating, has to have a constant angular momentum. If it is not, if it is not disturbed by any external torque. Imagine a universe, our own galaxy, which is not disturbed by any other external torque, and as it is rotating, those stars which are at the exterior or at the edge of our galaxy should actually be rotating at a speed, should actually moving at a speed which is far lower than the speed of stars which are at the center. And this can actually be explained just by taking note of the fact that you have constant angular momentum, and then you use L is equal to mvr square, and then you can actually prove it mvr, and then you use v is equal to r omega, and omega is constant because everything is rotating together at a given angular frequency. So based upon that, you can actually show that they should be rotating much slower. They should be moving. The linear velocity should be much slower. But instead, Zwicky actually detected that they were moving much faster than expected. And technically, that can only happen if there is matter around them. And with all the matter that we have evaluated and that we can actually see, this speed cannot be accounted for. So that is how we came to know that there has to be matter which we cannot see and which is causing this kind of rotation of a galaxy. This was one proof. Other proofs, there's gravitational lensing proof. It's difficult to explain right now what gravitational lensing is. There are proofs from several other.
I talked about it. I talked about it in the thing. Okay, so I think that's end of question.
Yeah. This is the end of the question session, and thank you very much, Ishwita ma'am, and overall, thank you very much to Chaitanya sir, so that he has joined with us, and thank you very much for your cooperation. And now, I would like to, yes.
So I would like to or say that if anyone has they need any help or about how to pursue a career in research, or they're interested to know more about this topic or other topics which are popular in physics, they can feel free to send me an email. I can send chat to everyone. Yeah. So I'll add my email address. Send an email, and of course, if you want to know about more opportunities about how to pursue your career, because there are a lot of outreach programs going on to encourage undergraduates, especially because they're looking for people, newcomers, with less experience, to give them more opportunities in all these internship programs. We have a lot of summer internships. Even in the pandemic, there are a lot of summer students working remotely in the collaboration. How I got it. And these internships are paid, so you don't have to spend anything. They'll take care of everything. They'll take care of your flight, your living, because they're advertising their experiment. So they're going to, apart from paying for your flights and everything, they're also going to give you additional stipend to survive. And so they are highly competitive. So you need to have the main point will be to have a very excellent recommendation letter. It doesn't have to, there's a misconception in India, people think you have to have a recommendation letter from a top scientist or something. That's not the case. You need to have a very good recommendation letter, a very personal recommendation letter, which highlights your abilities and everything. And thanks a lot. It was really nice about talking over my research.
Okay. Thank you very much. Thank you. Now, at the end of this, I would like to call upon Mahmuda Begum from our department to give the vote of thanks. Over to Mahmuda.
Good afternoon to all of you. Myself, Mahmuda Begum, on behalf of the Department of Physics, Lakhimpur Girls' College, take the opportunity to propose the vote of thanks on this webinar. First of all, I would like to extend sincere and heartfelt thanks to our resource person, Ishwita Saikia ma'am, for accepting our invitation and gracing today's webinar. Thank you, madam, for making very informative presentation and sharing your valuable time with us and making this webinar very interesting and meaningful. I also offer my sincere thanks to Sai Chaitanya Tedapalli sir for your cordial cooperation in answering the queries of participants. Hope the participants are very much benefited by your presentation. I take immense pleasure in extending our sincere thanks to our respected principal sir, Dr. Surajit Bhuya, for providing encouragement, guidance, and support. We are very grateful to Principal Sir for giving us an opportunity to organize this event. I also wish to express our heartfelt thanks to our esteemed participants, without whose active participation the webinar would have not been a successful one. Last but not the least, I thank to the entire team of Lakhimpur Girls' College, especially Parama Datta and Babishon Terang, and those who have greatly helped us in organizing the webinar. I once again thank everyone whose contribution has made this webinar a successful one. Thank you. Now I request Vinita Hazarika Madam to wind up the session.
Okay, thank you, Mahmuda. Thank you again. Now, with this, we come to the end of the session, and by thanking all of you present here again, and I declare that the session is over. Thank you all.